Hi everyone, welcome and thanks for joining this webinar today to talk about object storage with OpenIO SDS and Raspberry Pi. I am Mary Poncel, co-founder and VP of Marketing at OpenIO. Few points before starting, this webinar is recorded. The video will be sent and published few days after the presentation. If you have any question or feedback, feel free to ask them at any time in the GoToWebinar app. We'll be very happy to answer. I'm now happy to introduce our two speakers, who are Enrico Signoretti, Head of Product Strategy at OpenIO. Good morning, Enrico.
Good morning, Marie, and good morning, everyone.
And Romain Anciari, Co-founder and Head of Industrialization and Support at OpenIO. Welcome, Romain.
Good morning.
Good morning. So today the agenda is divided in three parts. First, Enrico will briefly talk about why OpenIO on ARM. Then he will describe what makes OpenIO SDS perfect for ARM. And then Romain will show you how to build an OpenIO SDS cluster with Raspberry Pis. And we'll finally have the Q&A session. So before starting, I would like to submit a very quick poll. So here is the question: is object storage part of your IT infrastructure strategy? It's already a part of it. We are looking into it. We don't need it anytime soon. We don't know yet. I'll let you a few seconds to answer. Okay. Okay, thank you very much. I will share the results at the end of the session. Okay, so I'm now letting Enrico starting with the first point. Go ahead, Enrico.
Okay, thank you very much, Marie, and welcome again to everybody. So today we are going to talk about ARM and object storage, but I want to spend just a couple of words about OpenIO. So first of all, what we do and what are the benefits. We are doing actually two things. One is next generation object storage, because we think we are setting us apart from the crowd of object storage vendors for the features that we have in our system and the capabilities that we provide to the customers. And on top of it, we developed a serverless computing framework which allows to build more value on top of the data stored in the system. In fact, we usually say to our customer that we can provide a better dollar per gigabyte for the data you store on our systems, but at the same time a better value for the data stored in the system. Consider that serverless computing, it's a very simple mechanism for which we can intercept everything, every sort of event that happens in the system, and trigger applications or just very short scripts to do operations on data or anything else. It includes image recognition, it could include video transcoding, it could include metadata enrichment, and so on. So why object storage on ARM? It's the question is quite important, because there are a lot of changes in the data center right now and in how we are thinking about infrastructure. If you think about the options that are available in the market, okay, for years we just had general purpose microprocessors. Okay, Intel is the leader here with the Xeon CPUs, and in fact they are very good for a lot of tasks. They are good for databases, they are good for even for CAD, for almost everything, but they are not specialized. Okay, it means that on average they are very good, but if there is a specific task you are thinking of, probably they are not the best choice. So ARM is gaining a lot of attention because it's a really efficient CPU in the mobile industry. You know, all the phones that are produced today are almost all the phones that are produced today are based on ARM, for example, because it's power efficiency. But it's not only that. The system of chips that you can find for ARM, so a complete computer in a single chip, are not only power efficient, but now they are more and more powerful. And that makes this kind of CPU very good for Internet of Things kind of devices, as well as for any other application that requires a small footprint, but also a great level of compatibility, because most of these CPUs run Linux. So it's a very, very flexible kind of platform. At the same time, there is something more that is happening, and you can think about the new tasks that we require to these CPUs, like, for example, virtual reality, as well as machine learning or artificial intelligence application. Okay, for this kind of application, you need even more power, and they are very, very specialized coprocessors. Okay, in fact, you can find in the whole industry cloud provider offering virtual machines with GPU or based on ARM or x86 or a mix of them, because depending on the application you are going to implement, there are specific features that are better for each, better implemented in each one of these systems. And there are new challenges posed by large-scale distributed architecture. Think about, for example, a server like this one. This is not one of the largest servers in the market. A few weeks ago, I found a server with 100 disks inside it. Okay, it's huge because it's more than 1 petabyte in a single server. Okay, and we really like scale out for all its benefits. But think about having a node in your scale out cluster of this capacity. If you lose the node just because the network is broken or the CPU fails, okay, you lose more than 1 petabyte. Even if you are talking about very large infrastructure, rebuilding 1 petabyte of data could be an operation that can impact performance. It could put you in danger to lose data and so on. So there are several reasons to rethink about how we are storing data in large distributed architecture. And it's not only about failures, so it is about power efficiency. Large data centers are looking to new ways to save power, or again, it's about management. Okay, there are several issues about this kind of systems. And the other thing is, again, that we have been talking about cloud for years now, but actually edge computing is again becoming relevant. Okay, so I'm not thinking about edge computing as it was thought a few years ago. So remote PCs or remote devices acting as clients for servers, okay, like terminal servers or so, but more in the fact that we have to compute data where it is created. Okay, so it is valid for IoT as well as for many other applications. So sometimes it is a question of latency. So the cloud is too far from where the data is created, so you have to compute it locally before sending it away. Sending only just result is much easier than sending away, you know, the whole data and get back the results. So for this kind of application, ARM is key, and because it provides all you need in a small footprint in any sort of device. And there are even more challenging fields now. Okay, machine learning and artificial intelligence. If you think about machine learning as a very, very algorithm and techniques that are based on the statistics, okay, and analysis, and you need a lot of data to make them work today. So it means that you need huge amounts of images to train your neural network for image recognition, for example, and and you need the CPU power to do all this work. So having a large scale repository with all your images and doing all this back and forth about reading images, computed images, find the result, save the results, and make it accessible to everyone. Okay, it's a lot of data moving back and forth. It's a lot of resources dispersed in the network. While if you can keep the CPU power close to the data, okay, all this process is simplified. It is possible to do more things quicker than in any other methods. So what's the idea here? So why we think we are perfect for RAM? Okay, there are some characteristics about OpenIO SDS that make the product perfect for RAM. Okay, it's for the first of all, we have a very lightweight design. Okay, last 2 weeks ago we were at a supercomputing summit in Denver, and we brought just 3 Raspberry Pi Zeros, okay, connected together in a cluster. So we were able to show a cluster made of Raspberry Pi Zero, which is a $5 computer, okay, and it's a very small device. The devices were connected via Wi-Fi. I know latency is not optimal, and it's not probably the perfect device to build a cluster. But again, think about a device of this size deployed remotely, okay, and a bunch of these devices deployed remotely. So you can build an object store everywhere. And the other thing is that by having the ability to fit all our code in a very small footprint, so we need just 400 megabytes of RAM to run all the object store, SDS object store. Okay, you can think about this kind of devices. This is a standard hard disk, except that in front of it we mounted a small PCB. This small PCB includes an ARM CPU, some flash memory, and 2 Ethernet ports connected to a standard connector that usually is used for SAS communication. Okay. By doing so, this very small computer, which is based on Linux, of course, and with the SDS installed, is a complete node. We call it the nano node, and it's self-sufficient. Okay, we just need 3 of them to make a cluster, but we actually installed hundreds of them in the same cluster. It brings a lot of advantages. For example, okay, power consumption. This device only adds 3 watts on the power consumption of a traditional hard drive. So at the end of the day, it's very, very efficient. But it's not finished there. You can, the software can potentially spin down the drive and turn it off, meaning that with this kind of technology, you can have a cold archive for a very, very low TCO, just because it doesn't, for example, consumes power. Okay, but data is accessible because all the metadata resides in the flash memory. So it is possible to query the storage without accessing the data, and when you need the data, you just spin up the drive. So it enables to build infrastructure that are very, very suitable for cold storage, for example. And again, the failure domain of this kind of design is minimal. So you don't need to do any sort of maintenance. If you lose the disk, you lose a node. If you lose the node, you just replace it. You don't do anything. You don't change RAM. You don't change network card. You don't need even a support contract. Just replacement. Part replacement is all what you know. So it changes, of course, the way you maintain your cluster, the way you support your cluster. Think about erasure coding, for example. So we have erasure coding, an algorithm that does distributed erasure coding across all the nodes. Okay, meaning that in a configuration like this, it is possible to lose 30 to 40% of the nodes before doing any operation, before risking to lose data. Meaning that it is possible to go in the data center just maybe once a month, even for very large installation, change the few disks that are broken, and that's the only operation that you have to do physically on the cluster. The other thing is flexibility. Okay, why we can leverage this technology? It's simple. So we think differently when compared to all the other object store in the market. Okay, first of all, we don't use the concept of the ring layout, okay, which is very common between other vendors. Okay, this ring layout is based on a distributed hash table, and it has a fixed amount of objects and metadata that are distributed across the cluster. Okay, for each single query, you have to ask to this table where to find the object. It poses scalability problems because the number of queries you have to do to understand where is the object increases. Sorry, not number of queries. The number of hops that the system needs to find your objects increases with the number of nodes, for example. Okay, so performance is not very consistent. We choose another mechanism, which is a system of distributed directories, which allows us to be much more consistent from the performance point of view, having the same scalability in terms of quantity of objects that we can store in a system, and a very distributed mechanism that allows us to take advantage of all the resources available on the single node, even if this node is very, very small. So by adopting this mechanism, we introduce the concept of the grid instead of the ring, which adds other advantages. One of the advantages we have is that we don't need to do rebalancing when we add new nodes, meaning that the node is immediately available, okay, and when you add it, and this is especially important when you add very small nodes, because if you have 1,000 node and you add 10 more nodes, doing a massive rebalancing, it's quite impossible. Okay, it could take days or weeks. With our technology, the new disk is immediately available, and we manage load balancing in a totally different way. So instead of having a fixed scheme of for load balancing, we have a technology called conscience. In practice, each single node computes a quality score that depends on the capacity available, network bandwidth available, CPU, and so on. Okay, so the score goes from 0 to 100. 0, the node is totally unavailable, it's turned off, and 100 is completely available. So when you add new nodes, what happens? The new nodes have much more CPU power, capacity, and network bandwidth available than anybody else in the cluster. So they will be hit more. Over time, these nodes will start to show, some stress on the resources. So they will, the conscience will decide to move some of the traffic to other nodes. It's a very simple mechanism, very efficient, and it is available for any service in the system. So not just for data, but also for metadata and all the other services that we provide. And on top of all of this, we have Grid for Apps. So it's our event-driven compute framework, meaning that we can intercept any event on the system and do operations, okay, directly on data stored on it. One of the most common examples that we show usually it's about image recognition. So for each single image that you store on the system can intercept the event, which is a standard write in object storage is a put, and when I intercept it, I can check if this is an image. I can run a script that does image recognition, and I can describe the content. This description could be part of the metadata of the object, could become part of the metadata of the object, and is searchable, okay? Meaning that you can search every image that you put in your system, for example. And this is just an example. You can do video transcoding, you can do anything else. And I think that with this, I want to conclude my part of the presentation telling you that with OpenIO SDS, it is possible to build large multi-petabyte installation. They can be geo-dispersed, so stretched cluster as well as replicated in different regions. But also, it is possible to install in very small devices our storage system and serverless computing framework, especially in devices that act like a data center. Like, think about a car, okay? So the car of the next generation cars, so the automated cars, intelligent cars, connected cars, they will have, yes, connectivity, but actually the connectivity is on a mobile network, okay? And even if we will have a 5G, consider a huge traffic jam, okay? How many channels will be available for communication? First. Second, not all the data that you are creating need to be moved to the cloud. Think about image recognition to detect if you are going into another car, okay? You have to do the image recognition, the compute, and just you have to save the log locally, and that log could be transferred later to the cloud. But there are many other information that you want to store locally, compute locally, and eventually move to the cloud, okay? Like diagnostics, information, logs, and maybe your dashboard camera recordings and so on. These are all valuable information. You want to store them, and you need to store them efficiently, and the best way to store them efficiently is probably on an object store locally, much better than any other system. You can't have a dual controller array in a car, for example, okay? Or even more so, it's interesting to have a serverless computing framework because you don't want to have an orchestration layer, a virtualization, complex application. You just need to run several small tasks almost in real time. And it is valid for any other kind of infrastructure that is now present at the edge. Think about an offshore platform, a remote plant, whatever, okay? And the good thing here is that the same technology that runs in the data center runs in the remote fields. So its replication is the same, as well as how we format data, how we manage data. So this is clearly an end-to-end solution that covers from the edge to the cloud. And I finished there, and I will pass the microphone to hand over the microphone to Roman.
Yes, great. Thank you, Enrico. If you guys have some questions about about this first part, please ask. We'll tackle them at the end of the presentation. And before starting the next part, I wanted to submit a second quick poll. So here's a question. What is your point of view about ARM-based architectures in the data center? It will never work. I'm skeptical, but I'll take a look. I'm open to anything that improves the infrastructure efficiency. It's the future, but I won't be among the early adopters. It's the future, and I'm craving for it. So I'll let you a few seconds to answer. Okay. Thank you very much. Romain is now going to introduce the next part.
Okay, guys. So here is the technical part of the webinar. I made a custom Raspberry Pi cluster, as you see on the screen. It's a cluster composed of 3 Raspberry Pi 3. It also works with other Raspberry Pi as well. So everyone can do it at home. So it's very easy. So to go through the installation process, we are using an Ubuntu Xenial 16.04 distribution, Linux distribution. You can find one for your Raspberry Pi on the website Ubuntu Pi Flavor Maker. That's where I took mine. It's very easy. I won't go through the installation process of Linux on a Raspberry Pi because it's not the topic here. And you can find a lot of documentation on this website or on the Raspberry Pi website. You just have to configure the Ubuntu server 16.04 distribution on your Raspberry Pi. Configure the SSH connection. So mine is configured with a classic Ubuntu user and using an Ubuntu password. So maybe you're asking why we're choosing Ubuntu instead of using the traditional Raspbian distribution that works very well on the Raspberry Pi. It's because we are using some package from OpenStack to provide the compatibility with the S3 and Swift APIs. And today, this package are not updated on the current stretch version of Raspbian as well as Debian, which Raspbian derived. So today we are using Ubuntu, and maybe in the future you can use Raspbian as well. And I hope it should be okay in a few weeks. My 3 Raspberry Pi are configured with only a very classic Ubuntu Server Edition, an SSH connection, and users and can do a sudo to execute command as root. I wrote documentation to explain everything. It will be available after the session. We will send you an email with everything to do the same. To make the demo here, I recorded the installation of my the installation of my cluster, Raspberry Pi cluster. Here it is. So we'll start and explain the steps we are going through. So first here, first here will be the setup of Ansible. So we are using Ansible at the moment. We are migrating, in fact, from Puppet, which is a configuration management tool, to Ansible, which is a tool very simple and very easy to handle. It can also install clusters easily, so that's why we are migrating from Puppet to Ansible. So the first steps here are to download the Ansible role. It's very simple. You just have to copy paste the 3 commands here, and you will get the open source roles. So everything here is open source to configure your Ansible environment. That's the first step here. Then we provide a small environment here to help you configure the Raspberry Pi, and you have just to switch the IP here. The default one are IPs, and you can use host names as well as other IPs depending on the installation of your current cluster. You can try your Ansible environment using this command, Ansible OpenIO -date. It will execute the date command on remotely on your Raspberry Pis, and if it's not okay, you can run a small playbook to install Python, which is the major problem when you are running a small image like this one, and so it takes a bit of time to install the packages. Okay, and after that you will be ready to run through the installation of the OpenIO SDS cluster. So it's a very simple command here also, the Ansible playbook, and you start the playbook named site.yaml. And here, Ansible will go through the classic installation of an OpenIO SDS cluster. So you have to configure the repositories to install then the packages. Package are install the package is taking a lot of time depending on your connection. So here the installation process is very quick. It's around it will take 3 minutes because I made it quick for the demo. But when you will do it at home, it takes 10 to 20 minutes depending on your internet speed connection, depending on the Raspberry Pi you use, depending on the speed of your SD card, and so on. So the process is going through configuring the packages and all the system. As I said, we are migrating from Puppet to Ansible, and today it's not we are not fully on. It's not an Ansible complete. It's not completely Ansible configured. So we are using an hybrid version. We use Ansible to manage the cluster more like an orchestrator, and we are still using Puppet inside to deploy the packages and manage the configuration. So it's an hybrid part. In the next month, I think we will drop totally Puppet, and everything will be done using Ansible. So here is the bootstrap of the namespace with 3 replicas, because it's a standard configuration to use 3 replicas. That's the final step here. And okay, it takes a bit more time. It should be okay in a few seconds. So the documentation is here. It will be available next days. We'll share it with you, obviously. As you see, there's a few commands to install a cluster. It's the very same system we use from 3 nodes to thousands of nodes. So it's here is an example with the Raspberry Pi, but we also are using this method for very large clusters with petabyte scale clusters, and that's what is nice with this method, you know. So your cluster is now ready. You see the recap of Ansible. Everything's fine. So now you will see the usage of it using AWS, the AWS client, command line client. Here it is. I'm using a personal Docker image to start AWS CLI, because AWS CLI is not available on my development system, so I use Docker for it. You can find it on my Docker Hub account. Here is a page, and we will share you the link as well. There's documentation to use it, and I'll give you here the command line to use with your newly installed Raspberry Pi cluster. So here we are. Up. So we downloaded the AWS client image. I'm starting with listing here my account. Maybe I will explain because it's going fast. So on the command line, you will need an access key and a secret key, like for every S3 connection. So here for this demo, the access key is demo, semicolon demo. It's the one we use as a default in our documentation. So if you're going through our documentation, this is the same for every deployment we made. So demo, and the secret key is demo pass. I specified a region here. It's a US East one, because when you're using AWS clients, it's usually the default region, and you don't have to change it. It's for ease of use. In our case, we support this image. This configuration is supporting only AWS S3 signature v2. For the v4, you have to install other components. And as it's not the topic here, I'll keep it simple using the AWS S3 v2 signature. You have to know we are also doing the v4, but it's more technical. Okay. You configure the endpoint. The endpoint here is it's on port 607, and I choose one IP of one of my Raspberry Pi cluster. You can choose any one of the 3 or more. And then I'm using the command line, so that's a S3 command, and I list the buckets. So my cluster is new, so I don't have any buckets now. First thing I do, I create a bucket named demo1. So the bucket is created. I will start again here. So create another one, demo2, it's created. Create a third one, demo3, it's created. Then I list, and I see I have 3 buckets named demo 1, demo 2, and demo 3. I list the first bucket. There's nothing in it, and I copy one file. So here is a etc password file into that bucket. It's uploaded, and now you can list it, and obviously, yeah, we will remove it. So it's removed. And then you can remove the bucket here. It may take more time because of the checks and the power of the Raspberry Pi. So this is a basic command of using AWS CLI. It works with other clients. You know, you can try CyberDuck or other clients as well. It will be the very same. In our documentation here, you will find a small documentation about the AWS S3 CLI. It's on our documentation website here. You can find docs.openio.io. Oh, sorry. So to make it directly without using the Docker and the usage here, a small usage, but you can find more documentation about AWS client on the internet, obviously. Here we are with the demo, and thank you very much.
Yes, thank you very much, Romain. So before starting the Q&A session, I would like to submit a very last quick poll. Okay, here's the question. How do you like to test the software like OpenIO SDS? So is it on my own hardware, bare metal, dedicated servers, like service provider, virtual machines, Amazon AWS or any other cloud, or Docker containers? So again, I let you choose one to answer. Okay, so I'm now going to take the first question. And Enrico, I think it's for you. When we'll see the nano nodes available?
So we are working with around the concept of the nanonode with 2 hardware vendors at the moment, and we will have a functioning prototype before the end of the first quarter, and the product will be probably available globally on the second quarter of 2018.
Okay, thank you. So the second one, I'm curious to know more about performance of this type of architecture. Do you have any information about it?
Yes, so we partnered with OVH last summer, and we realized the benchmark that is available on our website. And it is about doing the same thing that we did today, but with ARM server, dedicated ARM server available from this provider. And we started with 3 nodes, actually from these 3 nodes, and we managed to each one of the nodes as a single hard drive, and we moved from 3 to up to 48 nodes by adding nodes and testing read writes and all the other kind of metrics. So this is available in our resource page. So yes, it's possible.
Yes, and in fact, yes, in fact, I just uploaded this solution sheet document that we wrote with OVH in the GoToWebinar app. So in the document section, you can download it right now. Okay, the next one. So one of the main issues with Raspberry is input-output performance via USB. Any other option to build a cluster?
Yes. So we use the Raspberry Pi because it's the most common platform, and for a reason or the other, many people already own them. Okay, but there are other options in the market. One of our engineers built a cluster out of Banana PIs, which is a little bit more interesting platform because it has also a SATA port, so you can actually connect real hard disks to it, and the performance is much better because USB really sucks from the performance point of view. I don't know if Roman, you want to add something to this.
Yeah, as I see another question after it about the throughput we had with the Raspberry Pi. It's very small, effectively, because the IOs are very low on the Raspberry Pi. It wasn't designed for it, so it's not the best platform you'll have to run a massive cluster and get performance. There is other solutions. Yeah, the Banana Pi is maybe the best one at the moment. And for the number of disks,
so just to complete the second part of the question, what kind of disk did you use and how many?
So we didn't try a very large Raspberry Pi cluster, but like we said earlier, we did a benchmark on OVH with their ARM platforms, and the throughput was really great with it, with only 48 ARM and 48 disk, so SATA disk. You can check in the PDF for the numbers.
Okay. There is a last one. Is this install process running on one of the Raspberry Pis or on another management computer?
So here it was running on my management computer, so it's my desktop computer. But you can run it from another Raspberry Pi as well. It will be slower, I think, but it will work the same.
Okay, thank you very much. It was the last question, so thanks everyone for your time. Thanks Enrico, thanks Romain. If you want to continue the discussion, you can find a lot of information on our website, openio.io, and on docs.openio.io. If anybody has additional questions or feedback, please reach out. We'll be very happy to answer. You will receive the recording of this webinar and the documentation in the next few days. Have a nice day, everyone, and I hope to see you next time. Bye-bye.
Thank you.
Bye. Thank you very much.